Okay, today, for this set of notes, I'm going to go over the work problems. Now, we didn't get to go through all the examples in class, but I wanted you to have an opportunity to look all of them in your notes. And basically what we talked about is two ways to set up the equation. Way one deals with if two people start a job and finish a job together, then you would have together over alone of one person plus together over alone of the second person equals one complete job. Those fractions represent the fraction of work each person accomplishes on the job. The second idea is if one person starts a job and then a second person joins him, then instead of thinking about time together, you're thinking about the time that was actually spent by a person over how much time it would take him to do the job alone. And then the second fraction would be the actual time spent by the second person over how long it would take him to do the job alone. And again, would equal one complete job. So we've got Jane can wash the windows of a building in 4 hours. Okay, that is what Jane can do if she was all by her lonesome. And then Jim can do the same job in 6 hours if they work together. How long will it take them to wash the windows? Now, just on the outset, I'm just going to forewarn you, we may have to do, again, 2 parts to this set of notes because of the length of what the notes would look like. So I'm just going to list out the information that I find in this problem. So we've got 4, and that's Jane's time alone. So I'm just going to make it pithy, Jane alone. And then the next number they talk about is 6, and that's Jim alone. So we only have one more thing. What we don't know is how long it would take if they worked together. So I'm going to call that time together. Now, in a real problem, all you need to do is to write the x equals time together, or whatever the x represents in the problem. So what we're going to do is write a fraction of what Jane accomplishes on this job when the two of them work together. So together over alone, that represents Jane's work, plus together over alone, that represents Jim's work. That's going to equal 1 job. Now what we're going to do is figure out the LCD of 4 and 6, and that would be 12. And we're going to multiply everything by 12. So 4 goes into, let me do a different color, sorry. 4 goes into itself evenly and into 12 3 times. 6 goes into itself evenly and into 12 twice. That leaves me with 3x plus 2x equals 12. Simplifying, I get 5x equals 12, and then I divide both sides by 5. So what I don't do is leave an answer as an improper fraction. I need to change it to a mixed number, so that's something that's measurable. So 5 goes into 12 twice, which is 10 with 2 left over, and I write the remainder as a fraction, not a decimal, okay? Because if I get a repeating, how can somebody be doing something that is continuous forever? So I drop off the variable, and I add the label, and they were working in terms of hours. So that's how long it would take the two of them working together. And what you should notice is that that together time should be less than each person's individual time. Hence the reason why working together is a good idea. Okay? All right, next problem. We had Charlie and Denise mowing lawns. So Charlie and Denise together can mow a lawn in 12 minutes. So now notice the labels are minutes. Be cautious with that. Alone, it takes Charlie 20 minutes to do the job. So, working with Denise saves him 8 minutes. How long would it take Denise? To do the job alone? Okay, so let's go ahead and pull out pieces of data. So we had the 12 minutes, which is the time they worked together. And then next I see 20 minutes, and that represents Charlie alone. And then if you look here, how long Denise alone. So that's our unknown. We just say X, Denise alone. So process is the same. Together or actual time over alone, that represents Charlie, the amount of work he gets done. And together over alone, that represents Denise's work, equals one complete job. Now I've been asked, can I go ahead and reduce a fraction first so I have smaller numbers to find the LCD on? And the answer is sure, you can do that. I'm not going to show that. Just note that that is an option. And the reason why I'm not going to show that is that way, if you want to figure out LCDs quickly without doing any other steps, bam, this is it. So I'm going to multiply everything by 20x, and including this guy, and see what I get. So the 20s cancel on this one, the x's cancel, and nothing cancels over there. So my equation now is that 12 times x, 12x, plus 12 times 20, which is 240, equals 20x. So I'm going to subtract 12x from both sides, and then I'm going to use that symmetric property. I'm going to write the result of 20x, take away 12x, which is 8x, on the left, and I'm going to take the 240 and put it on the right. Divide by 8, and we get 30. And 30 represents the minutes it would take if Denise did the job alone. Okay? Okay. Example 3. We've got Andy takes 4 times as long to do a job as Bill does. Together they can do the job in 16 hours. So this must be a really big job to take that long. How long would it take each man to do the job alone? Okay, so the only number that I see in this problem that I can utilize for our fractions would be 16. And 16 is the time together. So I actually am going to get 2 unknowns in this problem, but they are related to each other. If you read the first sentence, it talks about Andy taking 4 times as long to do a job as Bill does. So that means Bill's time is going to be X. So that's Bill alone. Andy's going to be 4 times as long, so 4x is going to be Andy alone. So again, oops, I wrote that wrong. This is what I need you guys here with me, so I don't make dopey mistakes. That's time together. I know you're probably yelling at me now going, together, together, together. So we have together over alone, that represents Bill's fraction of work completed, plus together over alone, there's Andy's work completed, equals 1 complete job. Now again, you could reduce that fraction making it 4 over x, and then x would be your LCD, and you'd solve it from there. But let's just do it without reducing, okay? And we would have 4x would be the LCD. So we're going to multiply everything by 4x. So x cancels with x, 4x cancels with 4x. Leaving me with 16 times 4 is 64. Oops, I forgot to write over here. This was Andy. Plus 16 equals 4x. Now I'm going to use symmetric property. Write the 4x on the left. And the sum of 64 and 16 is going to be 80. Divide both sides by 4. And we get x equals 20. So what that says is that, well, let's do it this way. X represents Bill's time alone. So Bill would equal a 20-hour job. He could get the job done completely by himself in 20 hours. Andy, on the other hand, holy smokes, would take 80 hours. We're kind of joking in class that Andy's not the guy you want on your team. If you notice, the together time was 16, only 4 hours less than Bill doing the job alone. Andy, look at his time. He's the one that slows them down. So there's probably poor Bill trying to crack the whip on Andy. Okay? All right, next problem. This is another one that we didn't do in class due to time. We have Mike can paint a room. In 8 hours, and Ron can paint it in 10 hours. They work together for 2 hours. Sorry about that, wrong 4. How long will it take Ron to finish painting the room alone? Okay, so let's look at our data here. We've got 8, which represents Mike alone. We've got 10, which would represent Ron alone. And here's where it gets interesting. 2. That's how long they work together. So both guys have 2 hours as part of the time it takes them to get the job done. Now, what happens, it sounds like, is that at the end of 2 hours, Mike takes a runner. He goes on a break, whatever, and he never comes back. So, that's Mike's actual. Now, Ron, being the more responsible one, decides to stick around and finish the job, but we don't know how long that stick around by himself time was, so we write X. And that's going to be Ron's actual. So if we wanted to define X by itself, it would be Ron's additional time to finish the job. Now, when I write my fractions, the idea that they didn't work together the whole time doesn't change. Okay? It doesn't change. the denominator is always going to be how long would it take the person to do it all by themselves. The numerator is how long the person worked on the job. Now, when they work together, they work the complete job. So in this case, Mike worked for 2 hours, then disappeared. Normally, he would take 8 hours to finish a job. So his actual time over his alone time, plus 2 plus x over 10. That's how long Ron's going to work to finish the job, and normally he would do the job by himself in 10 hours. At the end of it, they've got one complete job. Okay? So we got to figure out the LCD. Oh, sorry, change my colors here. Of 8 and 10, and it's going to be 40. So we're going to multiply everything by 40. And this is a quantity now. So 8 goes into 45 times, 10 goes into 44 times. So let's see what we're left with. We've got 2 times a 5, which is a 10. Now we've got a quantity here, and we've got 4 times the quantity, 2 plus x, equals 40. So we get 10 plus 8 plus 4x equals 40. Combining up like terms, I have 18 plus 4x equals 40. Subtract 18 from both sides, and we get 4x equals 22. And then we divide both sides by 4. So again, we're not going to leave our answers an improper fraction. So we're going to do division. And 4 goes into 22 5 times, which is 20 with 2 left over. And then we simplify that down. So it would take 5.5 additional hours for Ron to complete the job. All right, I think I'm going to stop here, and then we'll do part 2. So come back and watch part 2.